Well, good afternoon. Why don't we go ahead and get started. I'm James McNames, and this is State Space Tracking. I understand there was a seminar that was scheduled for this room until recently, so if you're here for the seminar, you're in the wrong room. It's right next door in 155. Today I laid out the lectures with just an overview of what we're going to be doing. And today, I think probably for the first half of the lecture, we'll go through just an overview of how this course is going to run and what you can expect and how things are going to be different. And then for the second part, we'll get into estimation theory and actually get into some of the key ideas, the key foundational ideas that are for the duration of the course. This is going to be taught quite a bit differently probably than a lot of the classes that you've taken before. And it'll be more interactive. A couple of you were in the last course I taught on linear estimation and adaptive filters. And one of the things we did in that class is we had a lot of presentations, and the students really got to know one another. And that worked really well. I got great evaluations. The students all said they had a really good experience from that class. So I'm planning to use that as a model for this class. So I'm expecting all of you are going to get to know one another pretty well, I hope. And I would like to start off on this first lecture with just getting a round of introductions. So if each of you could say what your name is and what it was that drew you to this class, then I think that would be helpful for everyone, and especially for me. And Reed, since you're sort of the ringleader and one of the reasons that this class is even offered, maybe we can start with you.
I'm Reed. I'm a grad student in the Near Lab. I was interested in this class just because Kalman filtering and some state space tracking methods are really important in my research area, so it's really of interest to me.
Hi, I'm Nathan. I'm also a grad student in the Near Lab, and I was drawn to this class because Reed talked me into it. Also because I believe it'll be helpful with my research as well. I'm Eric. I work in the Near Lab, and I was interested in this class after talking to people who took it 2 years ago and highly recommended it.
Hi, I'm Adam Hanwerger, and I'm a grad student. I'm not in the lab yet. I'm taking it because Reed recommended it, but also I've taken 2 terms of control theory, and we touched on estimation in that, and I wanted to follow up on it. Sounded like a good sequence.
Great.
I'm Nehana, and I'm doing master's in electrical. I am taking this class because Reed recommended it.
You should be getting a commission.
Yeah, kickback.
I'm Ed King. I was interested in the class. I don't actually know that much about it, but it seemed interesting. I don't know Reed yet. I'm the first person that wasn't recommended this class, but so I'm interested in knowing more about what it is. I've read a little bit of the first book, the first chapter, and a little bit intimidated, but hopefully it'll get better.
It'll get better.
Me?
You?
Okay, so I'm Franco. I had already taken this class, actually, and I highly recommend it. But it was the first class that I took when I joined the Near Lab. And I haven't had time to talk a lot of McNames about this, but I was thinking if I can find the time, I think I would love to review the class.
Sure.
If it's fine with you. And I would highly recommend it. Whoever didn't talk to Reed. And it's very useful.
Okay. Hi, I'm Martina. I'm a postdoctoral fellow at HSU and working also with Ed. And I'd recommend the class. No. It's just personal interest, and I think it's going to be really helpful in part of my research.
I'm Elizabeth. I'm also a grad student in the lab, and Reed recommended this class. I'm mostly interested in doing the signal processing, and I thought this was a good class to take on that route.
Okay, great. Welcome.
My name is Jimmy, and I'm a grad student in the Near Lab as well. And I heard a lot of good things from a lot of different people about this class, so that's why I'm here. I'm interested in it because I don't know anything about the stuff that we'll cover in this class, so I'm just trying to learn as much as I can.
My name is Sam Henry. I'm a student in the NEAR lab, just graduate student in NEAR lab as well. I briefly attempted to take this class 2 years ago, and I really enjoyed the subject matter. I thought it would be a useful skill to learn, and so that's why I'm here.
I'm Scott Shuckleman. I work in the NEAR lab with Dr. Zert, and I'm working on a project for her to develop a Kalman filter, and so she suggested I take the class to kind of learn more about it.
My name's Jeff Hoffman. I'm a grad student and an engineer in Intel Labs, and with all the choices in signal processing on the curriculum, it was a hard choice, but I took this class anyway.
Hi, my name is Mika. I'm a EC graduate student, and I'm interested in the biomedical, so that's why I'm taking this class.
I'm sorry, how do you say your name?
Mika.
Mika. Okay, great. Good. Well, yeah, clearly, thank you, Reed, for rounding up so many students that expressed so much interest in taking this class. And I'll need to. You've also set some high expectations. You guys said such nice things about the last time this class was taught. That really sets the bar high for me. It's been a while since I've taught, and I like to experiment a lot. So if you're looking for a really polished class where I know exactly what I'm going to say and what you're going to say, you're going to find that that's not. One of the things I'm experimenting with, you can tell from the outline here, I'm trying to record this class. This is a new widget that I got for my new iPad, and theoretically, at the completion of this class, it'll record my audio, the slides, anything I write on the screen. I'll be able to upload it to YouTube. So although we're not in a classroom that has the usual distance learning cameras, this is far lower cost, and hopefully this will work. So this is an experiment, and if it doesn't work, then I'll switch to something else towards the end. This isn't my first time. This is an editing error from the first set of slides that I created it, but this is the second time that I've taught this class. What that means is that the lecture notes are still in rough shape, more or less, and you're going to be finding that I'm doing a lot of revisions and a lot of editing of the course content as we go through the term. There's also a lot of things that I wanted to change from the last time that I taught it. So expect the course, the lecture notes, and a lot of the content to be rough around the edges. And say a little bit about what state space tracking is. I realize now, based on some of the comments you made as we're going around and doing introductions, that I should have provided maybe a better overview of what kinds of things state space tracking methods can do and why they're so cool. What essentially you can get out of this class is an enticement to stay in it. And I don't have that with me, but I'll try to speak to it as we go through it. The entire class really is about these two equations. It's one way of looking at it. This equation is called the process model, and this is called the measurement model. I'll give you some other names for these equations now. You don't need to memorize that right at this moment. What we're essentially trying to do in this class is build estimators of the state of some process. So this is a set of random variables that change over time. And maybe to give a concrete example, actually I've got a nice example on my feet today, believe it or not. I've got on my feet a pair of inertial sensors that are wearable and they're synchronized. And in each of these sensors is a triaxial accelerometer, a triaxial gyroscope, and a triaxial magnetometer. And so I'm getting at a rate of 128 hertz, n is the time index here. At every time sample, these sensors are recording 9 different channels of data. And what I'm interested in estimating, the state at any given time that I'm interested in estimating, is where's my foot located. It's not what I measure, but that's what I want to know. It's how does my foot change over time. So where's my foot located in 3-dimensional space? And also what is the orientation of my foot in 3-dimensional space. You could think of that as trying to estimate 6 different parameters continuously over time. And it turns out that these parameters, the variables of the state, so you could think of this as a 6-dimensional vector, and the 9 things that I'm measuring with the sensors have a complicated nonlinear relationship. And that's what this function h of n represents, is it's the function that relates the state variables to what you can actually measure in some kind of process. And v of n, the second variable that's part of this expression, and all of these are multivariate. So you can think of x of n as a vector, v of n as a vector, and y of n as a vector. In the example I just gave you, this is a 9-dimensional vector, this is a 6-dimensional vector. V of n is another set of random variables that you can't observe that we use to represent the noise and the uncertainty in the relationship between y of n and x of n. So these sensors aren't perfect. They've got additive noise, they've got drift, they've got a number of things in them that make it even harder to figure out how x of n and y of n are related. And the reason this is a class on, well, I guess I didn't say that this was a class on statistics, but the reason that the prerequisite knowledge I'll get to in a few minutes that you should have as a background in probability and statistics is because of this noise term. It's the reason this isn't a math class where the problem is just a matter of trying to invert h of n. You can't invert h of n directly, even if you could solve the nonlinear equations, in part because there is this unobserved noise term that is unknown. Now, this could also, if we only had this equation, this could also be a class on just statistical estimation and not a signal processing class, because at any given time, the things that you're measuring only rely on the state at the current time. But one of the things that happens in most of the applications that we as engineers work on is that the state, we know more about the state than can be expressed by this equation. Usually we have some information, some prior information about the state that represents, for example, how quickly it can move. In the example of the sensors on my feet, I know that my feet move in a certain way and they only move so fast. They're not randomly jerking from one orientation and position at one time sample to the next being in a completely different position at a different velocity in a different inertial state. It changes slowly over time. And that knowledge that I have about human movement is represented by this equation. And this is where we incorporate that other information we have about the process, and in particular about how the state changes over time. And this also can be a nonlinear relationship. The relationship between the state at the next time sample relative to the previous time sample could change in a very complicated fashion. Typically that's a much simpler model than this model, but it doesn't have to be. And the techniques we're going to be talking about for estimating the state, given a sequence of observations, will work even if this is a really nonlinear function as well. Now, the way I move isn't predictable, and so the way that we model that uncertainty is to model that as a random process also. So U of n is a vector, a random vector, that represents the uncertainty in how the state changes over time. The state is not perfectly predictable, there's uncertainty in it, and we model that with the uncertainty with the noise and what we know about the dynamics with this general equation. So this entire class, when it comes down to it, is really about, given an application, how do you come up with these equations? How do you model it so that you can represent it mathematically this way? And once you get it into this very general framework, then how do you, what do you do with that? What algorithms can you apply, and what are the trade-offs in applying those algorithms to estimate what the state is over time, given a sequence of observations of what you can actually measure? Do you guys have any questions so far? I know some of you haven't worked with state space models before, and you don't have to have worked with state space models in order to understand this or how general this is. We'll be working through lots of examples in the lecture, and you'll be working through examples in both the homework and the project for this class, so you'll get it as we go along. This is my favorite body of methods for doing signal processing. For me, it's very appealing. I received my PhD in electrical engineering, and I specialized in signal processing, time series prediction, adaptive filters, and I've worked on biomedical applications of signal processing for many years. And what I did for years before I really got turned on to these techniques is use what I would call a heuristic approach. I knew about filter design, I knew about adaptive filters, and I could grab bits and pieces here and there and essentially build an algorithm, almost like building a block diagram, to estimate or detect whatever it was I was interested for a given signal. This framework of state-space methods uses a completely different approach. It's what some people call model-based signal processing, where the focus is really on coming up with these two equations and making sure that they're appropriate for your given application. Once you have those two equations, then there's a variety of techniques that we'll be talking about that you can use and apply to estimate the state for a sequence of measurements. This has a lot of nice features that are lacking in the heuristic approach. In the limit, you can show under certain conditions that the techniques we're going to be talking about are optimal. So if your state-space models are an accurate representation of your process, then you can actually say I have an optimal estimator in some cases. And that's a claim that is very difficult to make in general when you're designing signal processing methods. So, being able to make some claim about optimality is really compelling. These methods are easier to tune than a lot of the heuristic techniques where you've got knobs all over the place and you turn this knob and it might change how that knob should be turned. There are knobs. Part of the reason that we need you and we can't just say, well, it's done, Kalman solved it in 1969, is because there is some tuning of these algorithms that is necessary, as well as a lot of design in coming up with the right equations for both the so-called process model and the so-called measurement model. These techniques are also generally more accurate, one of the great things about this that we always wish we had, but we rarely have, is rather than just producing an estimate of the state, most of the techniques we're going to be talking about will also give you an idea of how uncertain your estimate is. So rather than just estimating, in the case of my tracking the position of my foot, halfway through my step that my foot is, maybe 5 centimeters off the ground, I can say 5 centimeters with a 95% confidence interval of plus or minus 2 centimeters, for example, about that. That's really powerful. You don't usually get that with most of the estimation techniques that we have as tools for doing signal processing. They're also more accurate. They can be very computationally efficient, although we'll start off talking about computationally inefficient techniques that can be quite accurate. There's a beautiful and very rich and very deep theory underlying these techniques. I should pause here for just a moment and say that this is not a theory class. This is a very applied class. We could have an entire year-long sequence on state-space tracking methods, spending, in fact, an entire quarter talking about the theory underlying all this without even getting to the linear Kalman filter. And we're not going to do that. If you're interested in the theory, I can certainly point you to references, and we could talk about doing a directed reading maybe as a follow-on. But my aim in teaching this class is that you walk out of here knowing how to apply these techniques practically to problems. We will be going through a lot of math. There is still some theory in this class. But my primary aim is that you're skilled in knowing how to apply these techniques, how to tune them, how to troubleshoot them, how to make them work with practical problems. Another advantage of these techniques is that they can handle nonlinear and non-stationary problems. And it's very unusual to come across a body of signal processing techniques that can handle either one of those, much less both of those. So there's a lot of great things about these methods. And I think the example of tracking the trajectory of my foot through a step with these wearable inertial sensors that are measuring something that's related to the position but are not directly measuring the position is a really nice example of where these techniques could be applied. And I may even show some examples of our work doing that. In fact, maybe... oh, nice. I just picked up recording, I guess, right where I left. So any questions about what we're trying to do in this class, what at root this class is going to be about? Is good with this so far? Okay. More about the class. I guess I already mentioned that we're doing model-based signal processing in this class. It's not the heuristic approach where you say, I'm just going to go directly for estimating the state using whatever knowledge I have. But in this case, we start by first building the statistical model that is comprised primarily of those two equations. And I think I already made a lot of these points. Oh, and one comment just at the end. It's easy to oversell any really cool and powerful technique, but it's not true that just anyone can apply these. It's not like, oh, the optimal algorithms are known, and now you don't really need an engineer or someone who's skilled in these techniques to apply them. You always, in my experience, you're never going to reach the state where anyone is going to be able to apply signal processing methods like this. It always requires some experience and knowledge and good judgment that you can only get from really understanding the theory and understanding how they work and how they don't work so that you can tune them appropriately. And then just a little bit about my background. I think I may have already made a lot of these points as well. In doing model-based signal processing, and in this case I'm showing a slight variation of what we had earlier. Rather than having nonlinear equations, we've got linear equations in this case. And this is what the Kalman filter was designed for. It's the case where there's a linear relationship between what you can measure in your state variable with additive noise, and that your state evolves over time based on some linear transformation of the state variables plus some additive noise. So I took a class on this as a graduate student many years ago, and the thing that always tripped me up is that we always started off assuming that we had those equations, and I was approaching this more from the standpoint of wanting to solve some practical problems. I was like, this class is worthless to me. No one hands me those equations. Where do you get those equations from? I can't do anything with this. And so I actually discarded that class and moved on to focus on neural networks and adaptive filters and other things, statistical techniques that I thought were actually useful, and rapidly just forgot about what I learned in this class. So I think that may be, I don't know if that's a common mistake, but by taking this class, I plan to answer the question and talk a lot about where do these equations come from? How do you come up with those models for a given problem? And how do you recognize whether a problem at hand is even appropriate for applying state space techniques? It's not perfect for all applications, and you don't want to use it to solve all problems. So being able to understand that is one of the things I'll try to convey in this class. As I mentioned, although today's lecture and lecture on Wednesday are going to be relatively traditional, where I'm doing most of the talking, and there isn't a lot of interaction, I expect that to change starting next Wednesday, when you all have completed the first homework assignment and you'll be presenting some of it. I would really like to have as much interaction as we can in the lectures. And I'm a big believer in a practice-first approach. I'd much rather that you guys had a problem at your fingertips that you maybe can't quite solve yet, or that you were trying to solve, and then you realized, oh, this technique allows me to solve those problems. So this will be project-oriented, and the homework problems will be very applied. And my hope is that by actually applying these techniques, that it's going to motivate and really solidify your understanding rather than trying to soak it all up based on what I say during the lecture. See, I think you'll actually learn more from the direct experience and from fighting with MATLAB probably than you're going to learn even in these lectures. So I'm planning to spend a lot of time this term thinking carefully about the homework assignments and assigning those so that they're interesting and that they are really helpful for you understanding how to apply these techniques. We'll start off with synthetic data, and I hope by the time we get to the 4th or 5th homework assignment, there will only be 5 or 6 assignments this term, that you'll be working with some real data as well and solving some real tracking problems. And I hope that you're applying them throughout the term and that you get started on your projects early. And as I've said it several times now, the student presentations I expect will be a significant component of the class. I don't want it to just be me talking. I found that I also learned about what I forgot to tell you when you echo it back to me and you get stuck, and I'm like, oh, I forgot to tell you that you got to do this, or you need to know about this idea. So it's been really helpful for me also as an instructor to get that as a source of going. Again, making the points before I get to the slide that has it on them. So again, significant component of the class, learning by doing is part of the approach I'm trying to use. I'm not looking for polished PowerPoint. One of the things that I'm thinking about doing that we're gonna try with the first homework assignment that is risky and you may hate me for, is that I'm not going to tell you who's presenting in advance. You all have to do the homework assignment, and you should all come prepared. So there is it's your turn, Sam, to present, that you can come up and we'll pull up your assignment because it will be submitted online, and you can talk the class through it on what you did and how things went and what you learned from it. We've got roughly 12 students enrolled, so each of you should plan on having your number come up twice over the course of the term. I hope you don't all drop because of that. We're not looking for polished PowerPoint here. The assignment, so long as it includes clear plots, answers the questions in the homework assignments, and is something that you're comfortable presenting is enough. So if you have other things to present, if your number does come up, and you want to present off of your laptop rather than off of the assignment that you submitted, then make sure that you email them to me. If you want to present slides and you think your number might come up, you can email them to me in advance, or you can plug in your computer here if you've got one with you. But I think in most cases, just your written assignment and bringing it up on the projector like we have here will be enough. Another thing that I'm doing in this class that you may also not like is that I'm teaching this class upside down. I did this the first time that I taught this class, and I thought it actually worked pretty well. The most advanced topic that we're going to be talking about in this class is something called particle filters. And it turns out with particle filters, you can understand them and apply them without first understanding the linear Kalman filter and then Synthetic Kalman filter and the various variations on Kalman filters. It wouldn't typically be done this way. In the book, it covers particle filters last. And I'm going to cover them first because I think these are arguably the highlight of the class, and I'd rather that you learn the most useful thing first, and we spent most of our time on it, and then we'll get to some of the more advanced topics later. This is also a project-based class. Half of your grade will be based on a project that you complete this term. And I expect many of you are going to be doing your projects using particle filters. So this really needs to be covered at the beginning of the class so that you can apply it in the second half of the term as you ramp up on your projects. So again, my high-level objective is that you know how to apply these techniques. You're skilled in the application of state space tracking techniques. And more specifically, if I had to narrow it down further, I would say that I want you guys to know how to drive a particle filter, which is the latest technique for doing state space tracking. And it's really cool. Here's a rough outline of what we're going to be covering this term. And it may not be in exactly this order. It's probably pretty close because I have done this one time before, but it's not perfect. So this week, again, more traditional lectures and doing estimation theory, which is the background for this class. Next week we'll cover optimal tracking, and then we'll move on to Monte Carlo integration, which is the basis for particle filters, and then we'll be in particle filters after, hopefully, just 2 weeks of lecture. So by the beginning of the third week, we'll be in really the meat of the content for the entire term. And then these are variations and generalizations of particle filters, other things you can do with particle filters as you go a bit deeper. And then we'll go back to the beginning as we get towards the second half of the class and go over the discrete time Kalman filter in some detail, and then some nonlinear generalizations of the Kalman filter called the extended Kalman filter briefly, and unscented Kalman filters. And this will probably be taught by Eric Wan, who recently joined the department. And if I timed things just right, there's 2 lectures that I currently have a travel conflict with, and I'm hoping I can line that up so it's when he can come and give the guest lectures. He's one of the the worldwide experts in sintered Kalman filters, it turns out. And especially for those of you who are in the near lab, he's someone that you guys should get to know anyway, because he's a local resource. And he also has some background in particle filters and knows the Kalman filter really well. So there's a lot of overlap in our knowledge. And then we'll talk about, at the very end of the term, when you're deep in your projects, talk about some specialized topics if we have time. We'll talk about something called marginalization, which is a way of blending the Kalman filter, the efficiency of the Kalman filter, with the nonlinear power and optimality of particle filters. So this is a way of blending the two. And then for a discrete variable case, you can use something called hidden Markov models. And so if we have time, we'll go over those as well. So again, second time I've taught this class. I've never actually taken this class as a student. I created it many years after I became a professor. We're in the second draft of the lecture notes. The homework and project assignments, I'm not assigning things out of the book. I usually find that the exercises in the book are often not applied enough, and they're too theoretical. They're often math problems, and I want you to have experience applying these techniques. The key thing, if you don't write anything else down in this lecture, write down the website, which is where all the course content is, including these slides. And my office hours are going to be immediately following the lecture. I'm available until roughly 2:30 each day of the lecture. I may be a bit winded, but I'm available. And if you want to meet me outside of class, then schedule a time by email with me to meet with me by appointment. It's a not good time to try to catch me is right before lecture. I'm one of those down-to-the-wire guys, and so I'm intensely trying to prepare to give you hopefully what is a compelling and sometimes entertaining lecture. And so I'm in the zone. It's not a good time to come and disrupt my concentration by asking me questions. So after lecture, or we'll also have a break, that would be a good time to chat with me too if you have questions or things you want to talk with me about. Let me show you the website. If you as I mentioned, Eric Wan, I expect will be giving at least 2 guest lectures, and I may have 1 or 2 other travel conflicts. I'll let you know when those are coming up. I think that will be an advantage. It turns out there's a lot of people in the area that are really good at state space techniques. Expected knowledge, we're going to be using MATLAB heavily. I know all of you in the near lab are MATLAB junkies. You must be to survive the near lab. And you should know how to use MATLAB and be fairly fluent in it. We're going to be using it a lot. I will provide some example MATLAB code, but if you don't know it, it's going to be hard, and you're going to have to ramp up on it really quickly. You should all have easy access to MATLAB since we have a site license for PSU. And I'm assuming that you've taken courses on, at least one course on probability theory, that you know linear algebra fairly well, and that you know the basics of signals and systems. So that's the prerequisite knowledge that I'm expecting you have. I've already gone over the course website and what's available there. And I've already talked about trying this thing with screencasting, so hopefully that'll work. And I've ordered a wireless mic, so as I walk around, hopefully it'll Bluetooth my voice into the tablet here. I don't know if it's going to work, but hopefully it will. Come on, take that away. Well, we'll see. I've already talked about MATLAB, and we've talked about the lecture notes as late as 30 minutes before the lecture. Some white space when we work through examples. The grading will be 30% based on the homework, and I'll say a little bit more about that in a minute. 20% will be the final quiz, and then 50% is for the project. And what I'm looking for is that on time you submit a complete project draft that is worthwhile for your peers in this room to review. It's not a good use of their time or yours if you submit something that's incomplete. So this 5% is based primarily on how complete the draft is that you submit at the beginning of dead week. The peer review is also based on thoroughness. So when you're reviewing other people's, whether you take the time to do a good job and give good constructive feedback that helps others improve their final projects. 10% based on the oral presentations you'll be giving. And those will be 10 to 15 minutes in duration each, and then 30% for the final report that you submit at the end of the term. Let me be honest, I'm not crazy about grading. It's not my favorite thing to do. And having limited time, I want to be upfront with you that in grading your homework, I'm going to be grading it primarily based on completeness. All of you, the reason this course is being scheduled is in large part due to Reed, but also because all of you expressed an interest in really learning these techniques. I'm assuming you're coming in motivated to learn, and you're not here just to get a good grade or for me to very carefully assess your homework and tell you, whether you miss a point here or there. It's not about certification, it's about learning. And I'd like to stay focused on that as well, which means that I'm not going to be spending a lot of time grading your homework. When you submit it, I'll go through it and look at whether you completed it or not, and your grade will be based primarily on how completed it is. That enables me to grade it more quickly, to more carefully design the assignments, and to more carefully design the content of the lectures that we're going to be going through. So I'm assuming with the homework that what you're getting out of it is an opportunity to apply the techniques that we're learning in the class, and that you're getting helpful feedback during the presentations. The grade, likewise, for the presentation is primarily going to be based on how well prepared you are, not on your mastery of the material, and certainly not based on whether you got it right or not. I'm looking at the homework as an opportunity to learn, not an opportunity for me to assess your knowledge, primarily. I know some of you are working professionals and some of you have many other obligations, and to the extent I can, I would like to support you so that you don't have to necessarily come and attend every lecture. It's one of the reasons that I'm screencasting. If you have to miss a lecture, I'm hopeful that you can still see what we went through and what was said about the various slides through the screencasting model. It's experimental. I don't know how well it will work. It certainly isn't perfect, in part because it diminishes the interaction that we have within the class. And so I hope all of you will make as much of an effort as you can to attend. There won't be any punishment, per se, if you don't attend, other than disadvantaging everyone just because there's less interaction as we go through some of these ideas, and especially as we go through the homework presentations. Everything's on Moodle. I'm not going to hand out any paper except for the final quiz this term. Will be the only piece of paper you receive from me. And likewise, I don't want you to submit any paper to me. I would like you to upload all of your assignments directly through Moodle. You can think of this as, it's not true, but you can think of this because PSU is so sustainable, if you like. It's not really my primary motive, but we can pretend that. The final report will be in an IEEE peer review format. These are the beautiful 2-column format that many of you, I think, are already familiar with, probably read, and some of you have already authored some of these. It's got to be, I've said it must be written in LaTeX or MS Word. If you can find another way to write it and upload it in PDF, that's just fine as well. But I think most of you will do it in either Word or knowing the caliber of the people in this room, probably many of you are going to be doing it in LaTeX. It's got to be electronic. I've got the formatting already posted on the website. And the scope should be similar to a long IEEE conference paper. I know some of the conference papers are 2 pages. I've said 4 pages is the length of the report for this term. I may expand that to 5 pages, but I'm probably going to keep it at 4. I'm still thinking about 4 or 5 pages, so I reserve the right to shift that a little bit later in the term after I give it some more thought. And the focus of those papers should be on applying the techniques, at least one of the techniques that we talk about in the class, to some real data, not synthetic data that you made up, but some real data from a real application that helps answer some kind of question. So what I'm looking for is applying it in a real application, one of the techniques we talk about. And probably for most of you, it will be some form of a particle filter. The textbook is relatively new. Ed's got a copy of it here, if you don't mind holding it up, just so the others can see it. I've looked at a number of textbooks. I like this one the best. It's got a really nice treatment of the Kalman filter. It also has a nice treatment of some topics that we're not going to be able to get to this term. in particular something called H-infinity filters. They're really slick, especially if you have an interest in controls. I like the notation and explanations. There's a lot of advanced topics, and yet it's also quite concise. As I said, you could take an entire course and just barely get to the Kalman filter recursions, and it really nicely and efficiently is able to get through the derivations so that you can start talking about how to apply it and what the issues are in applying it. It is heavy on terminology, and I don't think there's many errors in it. The first time I taught this class, there weren't many errors that were found, but I'm still not really certain of it. And it also has a great review of the prerequisite material in the first couple of chapters. If you're a little bit weak on the probability and statistics, it's got a really nice sort of summary of the key ideas that you should have learned in other courses. And as I mentioned, I especially like its treatment of the Kalman filter, and the extended Kalman filter and the unscented Kalman filter are really good. Unfortunately, the highlight of the class, particle filters, I haven't been able to find a good textbook that I really like. And so I'm going to be relying on the articles and on my lecture notes and on the MATLAB code to try to convey this to you. There are some statements and the way that he goes about explaining it with particle filters that I think is a little bit off the mark and more difficult to understand than some of the other sources that I found and then I've posted on the website. So that's a limitation. But overall, I think it's a good book, and I recommend it. Although, if you're a student eating, surviving on peanut butter and mac and cheese, you could get through this class without buying it if you wanted to. I'm not going to be assigning homework assignments out of it, and the reading is going to be pretty loose in terms of, so we're covering material right now that is in Chapter 8 rather than read Chapter 8, sections 1.2 through 1.3. So it's not going to be tightly coupled, but I think it is a good book and worthwhile. So. And then, as echoed by some of the comments that we started, this is challenging material, but we're going to be focused on application rather than on theory. These are some of the most advanced concepts that I've ever taught. So this is really advanced stuff, but I think it can be distilled, especially with good MATLAB examples, down to, and how do I apply this? What does this really mean in practice? How do I cut through all the math and understand what the key ideas are so that I can really apply these techniques appropriately? One of the reasons that I'm going to be relying on these student presentations is so that I can gauge whether I'm going too fast or too slow. When I give a lecture, kind of like what I've given in the first hour here so far, it's really hard for me to know, if you're quiet, are you getting it? Are you keeping up? Are you spacing out? Is it too much? Are you overwhelmed? And so the student presentations are an opportunity for me to see almost in real time, are you getting it? Are we on track? Or do I need to go through some of the other ideas maybe differently or give more examples or things like that? So again, I hope it's very interactive. And that's it for the overview of the class. That should give you a good sense of where we're headed, what my expectations are, and what the style is going to be. Are there any questions?
Do you list any readings on the website, or is it just we look up the topic and find a section in the book?
I can.